Hello, my name is Ashish. So we are releasing a course basically on the topic right now that I decided about the field. So this has the sequence of the lectures that we are going to make it by uh, targeting on this topic specifically D. D is the we have the regarding the fields. So we have the D1 is the gravitational field, and then we have the electric field, and then I'm going to start with the magnetic field. In the depth of that, we are going to be discuss about that every question, every topic that is going to be covered into that. Thank you. Let's start that. We are going to be start with the magnetic field. So what is a field is? Let's try to understand what is the field is. Field is the reason, it is a reason, even reason around you, where you can influence the things are. Just like your reason is your room, you can think like this: when somebody enter to your room, you're going to be say, no, you can't allow to that, or you have to sit it over there. You have the influence on that reason. So in the same way, we had the electric field, the concept, the same way we have the charges. So the charges have the influence, or if they have a certain reason, they can apply the force on the other charges. So that is the field of that charge. So a charge can apply the electrostatic force on the other charges. In the same way, we have a magnet. So if we have a magnet, that magnet can attract or the repel the other magnet or other magnetic materials when they are in that region of that magnet. So if you have the north like pole repel each other, unlike pole attract each other. So the idea is how they do that, because they produces the field around that, where they can apply the force to the other magnetic material. A magnetic material, I mean to say that it can be steel also, it can be iron. Iron is a good magnetic material. So the field is the region around a charged particle where it can apply the force on the um, other charges, that is the electric field. If it is a magnet, around a magnet we have the electric field north, or you can say originate from the north, go to the south. But do not forget that we will come to that point, they always make the closed loop. So this field is shown with the help of the magnetic field lines. And for a magnet, it will look like this. I'm making it inside the magnet also. Inside the magnet, it is a uniform magnetic field. Outside, you can say it originates from the north and goes to the south. So this is the north pole. It originates from the north and goes to the south. It always make the closed loop. So let me come to the some of the properties of that magnetic field. Let's try to understand that how you can magnetize a magnetic material. Magnetic material is the iron, is the best magnetic field. How you can imagine the things are. You can imagine that you had iron nail. So iron nail is made up of the small magnets. You can think it like this. The magnet has the north and south pole. So you can think it like this. These are the small magnet are disaligned right now. They are not aligned. So it doesn't behave like that. If I had this pen, this is made of the iron. So it doesn't behave like a magnet until unless I do not, or if I had to do something to magnetize it, to magnetize to material, to it acquire that magnetic property. To do that one, the simple way to do that one is you have some magnet and you rub this one in some specific direction. Obviously, in the real life, you have to do plenty of the time, more than the 50 to the 100 time in some specific order. Then these small magnets, or we specifically call them domains, they get aligned in the one way. So it will start, this iron nail will start behaving like a magnet. So we call it, they acquire that property. This is property, we call it a magnetization. We have the same time ferromagnetic substances The iron is the best example for the ferromagnetic substances, iron oxides. So all these magnets that you can see, mostly these are steel and iron oxide. Those are permanent magnets basically. They do not demagnetize easily. To demagnetize, I mean to say that when they lose their properties. So let's suppose that how they can lose their property by simply heating them. The domains get disaligned. Again, they do not behave like a magnet. So again, to do that one, I had to specifically again rub it in one direction. Then only it will again acquire that property. So by heating that, hammering that also, it can lose their deep magnetic property. They get disaligned on that. These are the how the magnetic field lines are visible. So when you have a single magnet, so this is the small one. So if I take the bigger one, that bigger one means that the density of the magnetic field lines will be more. So let me erase this one. Just look at that how dense they are, yeah, something. So if I take bigger magnet, so they have the density of that is the more one. So right now they are not giving the direction for that. To understand the direction concept, so you have to just from the positive it goes to the south. It originates from the north and goes to the south. It originates from the north and it goes to the south. Obviously, I can't show you the, but they always make the closed loop. They start from the north, they goes to this, and they come back and goes to south. So this is the concept that you have to keep in the mind. And it is inside the magnet also from the south to north. But it inside the magnet, it is a uniform. We are not concerned about that exactly in our syllabus right now, means how these are, but you have to just keep in the mind that inside that one, it is not. So due to the horseshoe magnet, north and south, we are more interested in the horseshoe magnet and inside this portion. It always goes from the north to the south. You can make it like this in a uniform pattern. So it goes like this also from the north to south. Remember it, they always make the closed loop. Again, it will go like this, south, inside the magnet. So this is the whole concept, we had to know about. So first one is it always originate from the north, go to the south. That's the first property. The second property, they always make the closed loop. They always make the closed loop. This is the second property that we have it, the magnetic field have. The third property is if they are more dense, look at that, they are more denser at the pole. So it means that it is the density is directly proportional to strength. It is going to be tell the more strength of the magnetic field at that point. So if it is a gap, as you can see, the gap between them is increasing. So it means the magnetic field strength is decreasing over there. So it is a outside a magnet, it is a non-uniform magnetic field. It is not uniform. So if you look at this carefully here, it is the more denser, so more strength it is of the magnet it is. That is third property. Fourth property is when you draw any kind of the tangent. So this is a compass that I taken it. This is the north pole of the compass, the red part, this is south. So if you put it the compass, basically you draw the tangent at any point. So I'm drawing the tangent at this point. So this is tangent drawn at the magnetic field lines will show the direction of magnetic field. So at this point, I have to draw the tangent. This is the direction of magnetic field. At this point, that draw the tangent, it will give the magnetic field direction. So, and at this point, so at any other point, you draw the tangent, it will give the direction of magnetic field. But toward the south, it goes toward the south. So you have to make it at this point, you have to make it like this. At this point, you have to show away from that. You can see that. You can put the compass at anywhere, it will give the direction at this tangent line. So at this tangent, this is the tangent that I'm drawing it. So this is a direction. So the red arrow gives the direction of that one. So at any point. So at this point, you can draw that tangent and you can feel that. This is every time you draw the tangent, that tangent line will give you the direction of the magnetic field. In the same way, the same concept for the electric field lines also we have it. So in the electric field lines also we draw the tangent that will give the direction of electric field. Here it will give the direction of magnetic field because these are the magnetic field lines. That is the fourth property that we have. So let's recap it again. The first one is it always originates from the north, go to the south. The second property is that we have it. They always make the closed loop. Fourth property, third property that we have it, the strength. How dense these magnetic field lines tell you the how strength it is. If it is more density, more strength of that one. Fourth property that you draw the tangent to that any of the point at any of the point, it will tell you the magnetic field direction in which the magnetic field it is. It will tell you that you can highlight that one. It is a continuous. It form a continuous closed loop. Then we have the magnetic field direction. These are the, you can mention that one. The strength represent the flux density, how magnetic flux density is. That is close shaped lines and something indicate that the field strength. Wider that is, weaker the magnetic field is. Tangent drawn, the direction of the magnetic field at the B at the point of the tangent to the field lines at that point. So you have to draw the tangent that will give the direction of the field. And this property that especially, this is also very interesting property that we have it. The fourth one is they never intersect each other. They never intersect each other. The two magnetic field lines never cross each other, basically. They never intersect each other in any of them. So I will show you the bunch of the other cases also. So it is going from the north to the south. It is north to the south. It is going from that north to the south. But if we had the two magnets and they are like pole, because like pole attract each other, you can imagine like this, the most of the magnetic field lines that are originating from the north goes to the south of the another magnet. So this is how the field get formed over there. So this is important for us, the how the magnetic field lines due to the two like poles. If you bring the two like pole each other, so it will be formed like this. And if I try to rotate that one, so you can see this one. So if you rotate this one, so I will come to it. So this is the thing. You can see that one clearly. Like poles, so the most of the electric field lines that are originating goes to this one. So, but if you had the unlike poles, let me show. If you had the like poles, sorry, then the magnetic field lines are like this. If you look at this carefully, they seems to be repelling each other. They are not crossing each other. Very important point. It is on the south, you can imagine like this, all the field lines are coming from the even making the closed loop and coming and going to the south. So you have to draw like this. So this is how you can imagine that one. And now, and this one, if I let's spin this one also. Let's take it. This is also north here, and this one is also north here. So then again, you have the same type of the formation because north is repelling each other. So, but the direction of the field lines are going to be changed. This is the direction of the magnetic field lines. So this is in the textbook that they shown it, how the magnetic field lines look like. So it is originating from the north and going to the south. And again, you can see if you had the like poles, it originates from the north, goes to the south. If you have the south, they are repelling each other. If even the south, north or the south have the same field.